In this lecture, we are going to do a little exercise that might help you in your implementation of epsilon greedy. This lecture is all about how to calculate a sample mean. Although it seems very simple, this lecture will introduce you to a very important concept that we are going to gradually build on as we progress throughout the course. Now, you might object to this and say, wasn't the sample mean part of the warm-up? I thought we already knew how to do this. And the answer to that is, just wait and see. First, let's start with a question you might have. If we're working with binary rewards that can only be 0 or 1, what is the purpose of having a sample mean? You might say, isn't the Bernoulli distribution a categorical distribution? In fact, you can prove to yourself that if the values of the random variable can only be 0 or 1, then the sample mean is exactly the maximum likelihood estimate of the Bernoulli parameter. Please try this yourself at home if you haven't done so before, or if you don't understand how this works. So now that we understand that we can unify real-valued rewards and binary rewards under the same sample mean calculation, let's talk about what's the best way to calculate the sample mean. Using the formula for the sample mean, you might suggest that this is quite obvious. Just take all the values of x that you've collected, add them together, and divide by the total number of x's that you have. The question is, what's wrong with this? I'll give you a minute to think about it, so please pause this video until you think you have the answer. Alright, so hopefully you thought about why calculating the sample mean naively might not be such a good idea. Remember that we are going to run our algorithms essentially forever. In order to run forever, we must have a forever amount of space to store those values of x that we collect. And obviously, our computers or our servers don't have an infinite amount of space. And even if they did, calculating a summation is O of n, so the more data you have, the longer it will take, and that will increase linearly with how much data you collect. Here's my claim. I claim that you can make the calculation of a sample mean, O of 1, in both space and time complexity, no matter how much data you collect. Again, as an exercise, before moving on to the next slide, I want you to think about how this might be the case. So please pause the video if you want to take a moment and think. Okay, so hopefully you thought about how you might calculate a sample mean using constant space and time. The key is that you can calculate a sample mean using the previous sample mean. Let's call the sample mean after collecting n samples, x bar subscript n. And this is so that the sample mean after collecting n minus 1 samples is x bar subscript n minus 1. We can write down both of these, which I hope is pretty obvious. Now that you know the main trick conceptually, let's make this an exercise. Can you express x bar n in terms of x bar n minus 1? Please pause the video until you've tried this on your own. Okay, so here's what you do. First, you can take x bar n and split up the summation so that you only sum up to n minus 1. Then you leave x subscript n by itself. This is just the last sample that you've collected. The next step is to realize that the sum of the xi's from 1 up to n minus 1 can be expressed in terms of x bar subscript n minus 1. We just have to rearrange the equation from earlier. It's clear that this sum is just n minus 1 times x bar n minus 1. We can substitute this into our expression for x bar n to get the sample mean at time n in terms of the sample mean at time n minus 1. One interesting thing you can do, although it's not totally clear why you'd want to do this at this point, is split this formula up as follows. The first step is to multiply out the 1 over n term. This gives us n minus 1 over n as the first coefficient and 1 over n as the second coefficient. The second step is to simplify n minus 1 over n to 1 minus 1 over n. The third step is to multiply out the x bar n minus 1 term and then combine the terms that have the coefficient 1 over n. At this point, you may or may not know why we did this, but that's okay. Just think of it as a fun math exercise, and we'll return to it later. So what have we learned in this section? We've seen that the sample mean at time n can be evaluated in constant time, and the amount of space we need to make this calculation is also constant. We only ever need to store a few things: the previous sample mean, the newest sample, and the number of samples we've collected. This by itself is quite useful, and should help you implement not just epsilon greedy, but many of the other algorithms we'll learn about. And although this is quite useful on its own, you'll see later when you study reinforcement learning that it actually goes much deeper.